in 2017 and delivered the 2018 Mary Cartwright Lecture for the London Mathematical Society. Since 2016, she has been a fellow of the Alan Turing Institute in London. Carola is also actively engaged in service work within the broader mathematical community. In 2021, she was elected as a council member at large for SAM, and she was named as a SAM Fellow in 2018. So it's my great pleasure to have her, and she'll tell us about mathematical imaging.
Thank you very much. Thank you so much for the kind introduction. Thank you for inviting me, and thanks everyone for coming and for meeting me over the day. So it was really very interesting to talk to all of you, and I'm going to talk to more tomorrow, which I appreciate a lot. I'm making a lot out of this visit. So right. So what I want to do is I want to introduce you within the next 50 minutes or so to the topic of mathematical imaging, which is what I've been working on for the last 15 years, and which is a research topic that is very close to my heart and that I love, in particular because, first of all, it has lots of different applications, and then, second of all, it can involve lots of different mathematical approaches, different mathematical themes that just pop up within mathematical imaging. So I think it's a fascinating field. So I'll start with thanks to my own research group. So this is the Cambridge Image Analysis Group that consists of postdocs and PhD students who are doing wonderful work. And a lot of what I'm going to show you, or actually everything that I'm going to show you, wouldn't have been possible without them. So it's really their work that I'm sharing with you today. So what do we do? And that is the first approach of trying to tell you what mathematical imaging is. So what we do is we develop mathematical methods and underlying theory based on various different mathematical concepts, frameworks. So PDEs is a very dominant tool for what we are doing. Also biased by the fact that I am originally a PDE person. Variational models, optimization, and then, as Jing Wei said, lately more and more machine learning is coming into the kind of toolkit that we are looking at. And we use and develop new methodologies based on these mathematical tools for solving various problems in inverse imaging, image analysis, and image processing. So ranging from image reconstruction from indirect measurements, such as they appear, for instance, in medical imaging, computer tomography, magnetic resonance tomography, these kind of technologies, they do not produce an image straight away. What they measure is some transform, nonlinear or linear transform of the image that you're after. So there is some process involved to extract a meaningful image out of these measurements. Image restoration, so that is denoising, deconvolution, inpainting. I talked to several of you about image segmentation and classification, so quantification based on imaging data, but also looking at dynamic imaging data, so doing motion estimation and object tracking. And so these developments usually in what we do happen very close to applications, from photography to remote sensing to biomedical imaging, arts restoration, forensics, material sciences, molecular biology, and so on and so forth. So lots of different things. I'll show you some examples in a moment. So again, what I want to do with this brief introduction, what I want to do is to tell you about mathematical imaging in general. What is it? Why are people excited about it? And what are the different types of mathematics that are popping up when you do mathematical imaging? And so I'll start telling you about mathematical imaging by just a definition, as we do as mathematicians, which is mathematical imaging is the study and development of mathematical methods for image analysis, image processing, and inverse problems in imaging. And what I want to do is to make this a little bit more concrete by giving you examples throughout this presentation. So what I want to discuss with you is what are the problems we want to solve, how can we mathematically formalize them, why do we want to solve them, and that's a personal thing. Why we want to solve them is because they're important in applications. Okay, you could also be interested in some of these questions in their own right because they're kind of mathematically interesting. And then I'll tell you about the different types of mathematics that pop up, and I'll give you one concrete example that is an example from a kind of framework of research problems that I'm currently most fascinated by. Okay, so that's what I'm going to finish with. And along the way, I'm trying to tell you the challenges and topics that are of current research interest within these different areas. So first of all, problems we want to solve. And all of this, again, as a disclaimer, is of course going to be flavored by the kind of things that I like to do, by the kind of things that we are doing in the Cambridge Image Analysis group. So it's a little bit anecdotal. On the other hand, we do lots of different things, so it will cover quite a wide range of things that people in mathematical imaging are doing. Okay, so making it a bit more precise, what is it that we are after? What are the problems we want to solve? And we can again summarize it in one sentence. What we want to do is we want to extract usually information from complex and usually imperfect data sets, imaging data sets, in an automated and robust way. Okay, so this is the basic information. You have a couple of examples here that are just for visual entertainment because I'm not going through them. I'm going to tell you now more systematically of how that could look like for different examples. Okay, so one big topic, as I told you at the beginning, is image enhancement, image restoration, and one kind of most widespread problem within this field is image denoising. Okay, and that can be very easily formalized as saying I'm measuring some noisy data that I call Y, that is the composition, and here I'm modeling it, for instance, as an additive noise component. It's the composition of a clean image U that I don't know, and a noise component, little n, and measuring Y and maybe knowing something about some distributional properties about n, I want to reconstruct U. Okay? By the way, all of this, I'm not really giving you any function space definitions or something like this where all these elements live. Usually mathematical imaging people are kind of divided in two camps, almost. One is the more analysis camp. Okay, the analysis camp will say Y, U, and N are elements in infinite dimensional function spaces, usually Banach spaces. And then we derive models to solve, for instance, the denoising problem in this infinite dimensional setting. So we come up with continuum models to solve this problem. And once we have derived the model, then at some point we discretize, of course, because we want to apply this to discrete data. And we want to reconstruct a discrete image. The other camp says all of these guys are just vectors, real or complex valued vectors, and discretize from the start. I'm more in the first camp because a lot of the theoretical results that we are deriving, and also the modeling is often much easier, much more amenable. So these objects are much more amenable to analysis and modeling in the infinite dimensional setting. So you can think of most of what I'm going to tell you that these are elements in infinite dimensional function spaces. Image reconstruction is a problem that is closely related to denoising, in the sense that again you're measuring some data and you want to reconstruct an image, only that in this case the data that you measure is not an image directly, but as I said is some linear or nonlinear transform capital T that is usually called the forward operator, light to the image U, and then I've again added some noise here. Again, this additive noise model is one choice, is the most common choice. Again, and in addition to this additive noise model, the most common choice is to say N is normally distributed and white. Okay, so that's usually the common assumption. But there could be other assumptions, right? You could have you could have multiplicative noise, you could have Poisson noise, you could have sparse noise. Yeah, so depends what your application is. Okay, and this second example is within the class of inverse problems, right? So this is already an inverse problem. You measure something, but what you're interested is indirectly hidden in these measurements, and you need to do some inversion to reconstruct the image that you're interested in. This is a typical example that appears in medical imaging that you need to solve. The other class of problems is when you have imaging data and you want to quantify something in this imaging data. And so one example is segmentation. So you have an image and you're particularly interested in certain objects in this image that you want to delineate from the rest. And you can formulate this as, say, you have an image U that is given on some domain, usually some rectangular domain. And you can, for instance, parameterize the segmentation as the characteristic function of some subset of this domain. Okay? And that is the thing that you want to find. Another example of quantification is classification. So you have an image. Again, this is one example. You have an image and you want to classify every pixel in this image. You want to give it a label. In this case, these are different land covers. This is a satellite image. Or you have maybe, this is what is written here, you have a data set of images and you want to assign to each of these images a different label, right? Just trying to get you in a bit more systematic thinking about the kind of things that we want to solve. Why do we want to solve them? I mean, some of them you might have seen hinted already in the pictures that I've given. This is an example that the one here on this first slide, that was one of my first interdisciplinary collaborations when I started in Cambridge, was together with a zoologist there, who was interested in so-called pied flycatcher birds. I don't know if anyone knows what these are. These are birds that commute. And she had this hypothesis, so they came to Cambridge for breeding, and there were breeding boxes a bit outside of the city. And she had this hypothesis that the male birds, they had this blaze, this white blaze on their forehead, and she had the hypothesis that the size of the blaze is correlated in some way with their sexual productiveness. Okay, and she wanted to quantify that. So what she did was that she went to these breeding boxes. She did that all by herself, by the way, which just looking at the pictures maybe is already quite impressive. She went to the breeding boxes, she caught the bird, she took the ruler, she took the camera, and then she took pictures of these birds. Right? Okay, and then what we did might be obvious, right? So we had to quantify that. Unfortunately, the end of the story wasn't that interesting in a way because we couldn't support her hypothesis. It wasn't significant enough. So, but it was still a super cool project. So again, let me tell you the type of problems that appear in the different fields. So biomedical imaging in research, as well as developing clinical support tools, is definitely a big area of need for automated image analysis methods, as well as for methods that can get the most out of the data that's being measured in the hospital. Okay, so the first two examples are again along these lines of getting the best images out of data, right? And I'll go a little bit more into this topic later. This will be my example that I'm going to show you. How to get the best image out of data depends a lot on the mathematical model that you use, the prior assumptions, and how you model them that you have about the type of images that you reconstruct. And then a lot of quantification, helping researchers as well as clinicians to quantify things in images, right? So this was a collaboration with people in biology who were interested in the movement of these what they call comets here in this Drosophila oocyte. This was a collaboration with people in cancer research who were interested in the effect of antimitotic drugs on cancerous cells, right? So chemotherapy drugs, basically, and they were interested in the effect that these antimitotic drugs had on the mitosis, so that they really attenuated the mitosis of the cells, and we helped them with that. And then, of course, the big thing is helping radiologists, right? So segmenting tumors and so on. So a lot is really helping to replace lots of manual work that is tedious and not interesting to just replace this by something automated. And then this goes more and more towards clinical support. Of course, where nowadays image interpretation, image analysis methods have more and more impact is in finding patterns in large data sets, right? So helping clinicians to take advantage of all this knowledge that is, encoded in large databases of clinical data and imaging data of some, they see a new patient and they can match this patient to a database of other individuals that this hospital or maybe another hospital or somewhere in the world someone has seen, right? To find similarities and learn from the path, from the disease path, for instance, or the treatment path that someone else has had. Another area that, again, has lots of problems, lots of really fascinating problems, is remote sensing. So observing our Earth, basically, through satellite imaging data, through airborne imaging data, or even through just UAVs that are being used more and more nowadays. So helping to extract information from this kind of data also is a big and interesting application area. Here, and by the way, also in biomedical imaging, what also is an interesting topic of research is how to fuse different types of data that is being measured, right? So in medical imaging, you could say you have a CT image of someone, you have an MRI image of someone, you have a PET image of someone. How do you actually correlate and make the most out of this information to look at that together, right? And the same is, of course, also when you think about remote sensing, right? So you have LiDAR imaging data, you have hyperspectral imaging data, you have just airborne photography, so RGB imaging data. How do you fuse these different types of information that might live also on different spatial scales, on different temporal scales? And then just to contrast things a little bit, digital humanities is coming more and more as a topic of interest within mathematical imaging, just because museums are digitizing more and more of their artwork, and also because museums are doing more and more scientific imaging themselves, right? So they're again measuring their artifacts more and more in different ways that let you look at what is not visible to the human eye, look at these things in different ways. To, for instance, detect underpaintings or remove overpaintings, like in this case, digitally restore paintings, or in this case, illuminated manuscripts. Or this was a nice pet project of one of my former PhD students who worked on 3D conversion, so converting 2D movies into 3D. And he just did that for one of these illuminations, which was quite nice. Okay. And then there are many, many more, right? And again, these are just anecdotal: material science, computational fluid dynamics, molecular biology. I mean, I'm sure if you're interested, if you're working in imaging and you're interested in one kind of discipline to collaborate with, you will find an imaging problem there. Okay, so this is now, what do we usually want to solve? Where do these problems appear? And now, how do we do that, right? And again, there is loads around, loads of different approaches, loads of different types of mathematics that appears when you want to solve these problems. So nonlinear PDEs and variational calculus is a big topic because, well, based on the assumption that the main characterizing structures and images that really make up the content, and in particular, when you think what you want to do with the image is to quantify something in it, like you do in research, usually if you want to do some, if you do scientific imaging or medical imaging, is actually geometric, right? So edges and curvature and things like this, these are geometric properties. And PDEs are really good in modeling geometric properties. Okay, so this is why they appear. And they're usually nonlinear, well, because edges in the continuum are discontinuities in the image function. And so this leads you to non-smooth variational problems and nonlinear PDEs. Applied harmonic analysis and approximation theory pop up, well, because, you know, as a kind of counterpoint to the PDE geometric viewpoint, you can also have the viewpoint of the kind of multi-resolution analysis viewpoint to say, I assume that my image is can be sparsely represented in some kind of dictionary or, you know, basis or whatever you have. And so this is this viewpoint, and then you ask yourself, how well can I approximate it under these assumptions? And under these assumptions on the data, and under these assumptions on the kind of sparsity level that this image has. Numerical analysis and optimization, of course, appears because, well, at some point we need to discretize our PDE or variational model, and we need to solve an optimization problem or solve this nonlinear PDE. And again, usually these type of numerical analysis and optimization approaches are non-classical in the sense that we're dealing with non-smooth optimization problems and nonlinear PDEs. So, yeah, I'll say a tiny bit more about that later. Differential geometry also appears because a lot of times the imaging data that we measure or the image that we want to reconstruct doesn't live in a linear space. Statistics appears, well, because randomness is contained in the data. The moment you have noise, there is randomness, and so, you know, any kind of randomness will require some statistical considerations, some distributional modeling, and so on and so forth. And then machine learning, of course, as you might guess, has been, I would say, really impacting the field of mathematical imaging for the last 10 years or so. Before neural networks appeared, people played around with support vector machines and things like this, but it didn't really have a huge impact there. So really before deep learning appeared, most people didn't look at learning at all, right? So most people really developed these denoising or segmentation approaches out of first principles. Okay, really thinking about how to model structures of images and so on and so forth. Now, since deep learning, things have changed a bit. And then there are many more, right? Stochastic analysis, topology, numerical linear algebra, you name it, right? So yeah. Okay, so now I want to dive in, and I want to give you an example out of this that takes you from nonlinear PDEs and variational calculus all the way to machine learning. All right. Okay, so right. So, okay, let me maybe start like this. So, where I think the most exciting mathematical questions at the moment arise within mathematical imaging are at this interface between mathematical modeling and, in particular, analytic approaches like PDEs or variational models, and machine learning, in the sense that we have done a lot of good work without machine learning for many, many years. But one of the things we have done a lot of work on and still are not very good at is characterizing what images really look like. I'll make this more precise in a moment. On the other hand, deep learning neural networks are very, very good in extracting, characterizing information from data sets. And they have a very good handle on characterizing what images look like. And so this is where the two worlds kind of come together, and where the challenges lies to bring them together in a way such that you still have a rigorous mathematical foundation for the methods that you're developing. Yeah, because as we know, the moment neural networks appear anywhere and they come into what you're wanting to do, like poof, like all the kind of theory and so on goes out of the window, right? So, doing this in a way that preserves that, I think is very important. Now, the starting point again is mathematical analytical models, and so let me say a few words about those. So one of the most widespread approaches within inverse imaging problems, or actually image analysis, image processing in general, are variational regularization models. Okay, so here the idea is, and I'm just showcasing this now for image denoising. So this is our image denoising problem that I've defined at the beginning. Now, the variational regularization approach is casting an approximation to this image denoising problem as a minimizer of an energy function, usually, that classically follows a very kind of precise framework of how this energy looks like. The energy is usually split into two parts. One is the data discrepancy or data fidelity term that tells the minimizer that the minimizer being the reconstructed denoised image, that it should be close in some way to the noisy image that you're measuring. Okay, so for instance, this could be just the least squares fit. Okay, but then since you want to denoise, you want to get rid of the noise, you need to regularize. You need to have a smoothing term also in this energy, and this is what this regularization term here is doing. With some weight in front that will depend how big your noise level is that you have in the noisy image. So the more noise you have, the larger your alpha will be. And so this regularization term is usually based on norms of derivatives of u, for instance. So this is a typical thing, again, that connects us a bit to PDEs. Because as you can imagine, if you are penalizing the derivative, so the derivative is nice because it gives you a spatial, it connects basically the intensity in one point, so the intensities of your neighbors, so it gives you a spatial awareness of patterns that are happening around you. And then the norms that are usually chosen are the most typical one is the L1 norm that encodes some kind of approximation to sparsity assumptions that you have about the type of images that you reconstruct. Yeah? So you can think of the regularization term both as a smoothing procedure, but also as a procedure to restrict the type of least squares fits that you make to your noisy image, to restrict it to a subset of, let's say, a subset of L2 that is a subset that fulfills the prior assumptions you have about the image. That could be, for instance, that the image is sparse in the gradient. So the gradient of U is 0 in almost all places and just non-zero in a few characteristic places. Okay? You can also think of, in particular, this one. You can also think of this, again, in the infinite dimensional setting as the total variation. How many of you have heard about the total variation before? Oh, that's perfect. Okay, so quite a few. And the total variation in this case is a nice regularization term because it really lets you characterize discontinuities, right, in the minimizers. And again, it preserves the edges in the image while smoothing out small oscillations. Okay, so that particular regularization is called the total variation regularization. Or the Roth model in the context of denoising is also called the Roth model, since we're close to UCLA, I should also say that. Going back to Rudin, Osher, and Platini. And here is why, the kind of effect that these variations, so the kind of solutions that these variational problems deliver. As a simulated example. So this is the original image. Here I've added just some Gaussian white noise to the pixels. And here you see two solutions of such a variation regularization approach. One is with an H1 semi-norm, and the other one is with the total variation. You can see that using an L1 type of regularizer definitely makes a difference in that in the preservation of edges in the denoised image. Yeah? You might like one or the other, the left or the right image better or less. Might even be that you like the H1 semi-norm image more. But for quantification, and this is why the total variation has been so successful for a long time, for quantification, getting an image like this is much, much easier. Okay, so this is why total variation regularization has been so popular. Okay, let me skip that. We just talked about this before. What is the connection to PDEs? Well, basically just by the gradient flow or the corresponding Euler-Lagrange equations. So if you want to, either you can think of it as characterizing solutions to your variational problems, or you can think of it as iterative schemes to compute minimizers of your variational problem. What you get are PDEs. So if because this is a non-smooth problem, if you can't just differentiate that, you can't just take the classical gradient. What you need to do is take subgradients, which is the equation that I'm writing down here. This is the subdifferential of the total variation. If you don't know what that is, let me make this a little bit simpler. You can also try to differentiate it where you can actually differentiate. namely outside of 0. And then you get a particular subgradient which looks like this, where you can again see the effect of the total variation regularization. Okay, so meaning that if the gradient of u is large, if the absolute value of the gradient of u is large, you diffuse more, and if the absolute value, you diffuse less, and if the absolute value of the gradient of u is small, you diffuse more. Okay, which is exactly what I said, that you diffuse less where really structures are that you want to preserve, and you diffuse more the rest. So what you can see here in this little movie is where I'm showing the evolution of this equation starting at t equals 0 just with a noisy image, and choosing an alpha that is much too large. Okay, so you usually would choose the alpha, by the way. Yeah, you would usually choose the alpha such that the stationary at the stationary state you would get a denoised image that you like to look at. Here I'm choosing it too large just to show you the effect. So you can see exactly this kind of smoothing effect, yeah, of what the total variation is doing. That's doing this nonlinear smoothing. Okay. So the nice thing about these type of approaches is, and again I'm sticking here a little bit, this is flavored by this total variation regularization model, is that they come with a lot of both analytic properties for the continuum model, both in terms of, just typically well-posedness results that you can get, but also qualitative results. So for some so for some given noisy images, some simple ones here that are, for instance, characteristic functions of convex sets with Lipschitz continuous boundaries, something like this. Yeah, so you can explicitly compute what the minimizers look like. So you have some, you can derive some qualitative behavior of what total variation regularization is doing, or there are results that say if you apply total variation regularization to a function, it will always diminish edges. It will never introduce new edges in the image. Things like this, right? So you can prove things about minimizers. And various different types, just to highlight again the various different types of mathematics that appears, right? So from PDE analysis to geometric measure theory, all the way to kind of viscosity solutions of PDEs, all of this kind of appears there, right? And then on the numerical side, the moment you want to solve these type of problems, again, as I've said earlier, this is kind of all non-standard in the sense that we have non-smooth minimization problems, we have nonlinear PDEs. So all of this uses tools from convex analysis and from sometimes also non-convex, non-linear optimization, and also some of these approaches. One of the problems often with these approaches also is in particular in the context of imaging, where data sizes are usually huge, okay, especially since technology is getting better and better, that of scaling with the size of the data. So also numerical questions like domain decomposition, subspace preconditioning, and things like this come up, stochastic optimization, and so on. Okay, so we have quite a handle on how to deal with these type of problems, both on the analytic and also the numerical side. And they can be generalized not just to denoising, but to other types of forward operators. And here you just have a few examples, right? So image in painting, I've talked with some of you about before. For image in painting, what you would just have here is a projection. So in your data discrepancy term, a projection onto the part of the image that you know, right? Outside of the hole that you want to fill. So the projection operator for image deconvolution, you would have a convolutional operator here. And then for instance, for computed tomography, you would have a Radan transform here. For magnetic resonance tomography, you would have a Fourier transform here, and mostly subsampled versions of both Raman or Fourier transform. Okay, because usually you undersample when you're measuring because of time constraints, or usually because of time constraints. Okay, and this is just an example where I show this whole evolution now, but for imaging painting with the total variation. Okay. And then the total variation is just one example, right? So a lot of what people have been doing, apart from deriving analytical and numerical results for these type of problems, is to come up with new type of regularization approaches, right? So we have seen at the beginning with this cameraman example that depending on how you choose this regularization term, the result looks very different, right? Both of these results fit the original noisy image in exactly the same way, right? So they are both plausible solutions to the problem. What differs is the prior assumptions that you put in, right? And so lots of people, the prior assumption being how this image looks like, right? How the different structures can be represented in a mathematical way. So lots of different types of regularizers have been proposed. And I'm just going to show you this short video to make a point of, well, kind of have a bit of a break for a moment and to make a point of what that means.
Hey, Carola.
Hi, Samu.
Hey, you know how to remove things from photographs, right?
That's right.
Can we try?
Sure.
Can you make the coke disappear?
Okay. Watch it.
All right, pretty good. I think I can still see something.
Yeah, that was harmonic in painting.
Okay.
We can try total variation in painting.
All right.
Okay.
Oh, pretty cool.
Isn't it?
All right. Can we try some more stuff?
Yeah, that would be fun.
All right.
Let's do it.
Try it. That was all pretty cool.
Yeah, that's the power of applied mathematics.
But can in-painting make us disappear?
Sure.
I mean, that wasn't absolutely necessary for the talk, but I mean, as a side thing, I think it's nice to demonstrate that what you put into as prior assumptions really makes a huge difference, right? And it was definitely lots of fun to taking this. By the way, did anyone recognize the place? I don't know who has been there before. Anyone? So this is kind of the kind of holy grail of mathematics in Germany is Oberwolfach. So this is in Oberwolfach. This is in the mathematical institute there. So yeah, so it's quite nice. Yeah. Anyway, so it makes a difference, and I mean, with the inpainting, we haven't been doing too badly. All of this was non-machine learning based, right? But even for the best method, right, this Newton approach, this patch-based, you could see with the snowman in the end, I mean, it has some limitations, right? And this is where the machine learning idea comes in, and this is where I really think this can make a huge difference, is that, I mean, the main reason why we have been always struggling with characterizing images is because the nitty-gritty details of images are just very different from one kind of area to the next one. Yeah? So while, you know, saying edges are super important, and this is where we should focus on, actually it is not the whole story, right? And for instance, even if you go beyond the visual effect, right, you could still say, well, okay, I mean, visually this inpainting maybe could have been better with something that has a better characterization of images, but maybe total variation regularization would have been fine to just get the main parts back that are important for identifying what it really is in the image. It's not true in all applications. So for instance, also in medical imaging, edges are important. But what also radiologists do, for instance, is radiomics. I don't know if people heard about radiomics. What is radiomics? Radiomics is when they, for instance, look at, so they segment tumors. Why do they segment tumors? Not just because they want to look at the size, but what they also do is they do statistics. So radiomics basically just means they compute some statistical properties of the intensity distribution of the image function within the tumors. Okay? So they look at the texture basically also within the segmented regions, so they do look at fine scale details as well, right? Anyway, so defining prior information, I think this is where learning from data, in particular with neural networks, can have a huge difference. And so this is one way, I think, that it is very promising, and that I will briefly tell you about, that we have been doing, which is, in this variational context, learning the regularizer. Okay, so just leaving everything else in place, but learning the regularizer in a way that still gives us a nice variational problem that we can solve in the end, right? That has some possible convexity properties, that has some well-posted properties, and some also properties that usually inverse problems people like to have. For instance, what they call convergent regularization, which means a rigorous regularization approach within inverse problems needs to be one where you can say when the noise level in the data goes to 0 and the regularization parameter here goes to 0 also at a rate that depends on how quickly the noise level goes to 0, then my solution to the variational problem should converge to the ground truth. Yeah? So things like this is what we like in approaches, and so this is what I'm going to briefly tell you now with our learned regularizers. So this is joint work with a couple of people. The main person with whom we started this is Sebastian Lunz, is a former PhD student of mine, and then along the way several people joined. Jeremy is now a lecturer at Birmingham. Marcello is at the University of Twente in the Netherlands. Søren moved to the dark side to work for a hedge fund. Shubo is at an IIT in India. Ozan is a professor at KTH in Stockholm, and Sek is a current PhD student of mine. Okay, so the idea here is we want to learn a regularization. I'm going to exemplify this for computed tomography. So just to remind you, in computed tomography, this forward operator capital T is now going to be the radon transform. Okay, so meaning what you see here, the measurements on the right, in the simplified scenario of thinking we have a 2D object that we are doing tomography of, right? That we are measuring line integrals through this image intensity functions at different angles. Okay, so let's say at this kind of 45-degree angle and at different positions. Okay, so one parameterization here is the angle, and the other one is the position of the line. Okay, and based on these measurements, and then I have noise, and often also when I say subsampled, is that mostly what is being subsampled is in the angular direction. Okay, that you're not measuring at all the different angles, so all the different meaning as many unknowns as you have in the image, you would like to also have in your measurements. So again, what you do is you solve this usually with regularization, right? And now I want to solve this with a learned regularization approach. And so the question is, how do you train a regularizer, right? And so what we did, and this is again the beauty coming back to analysis, is that we trained it as a minimizer of the Wasserstein distance, right? So why is that a good idea? So what we said was, what we really want the regularizer to do is, if you think of it, right, the regularizer should penalize the type of solutions you want to discourage, and it should encourage the one that you would like to see, right? So it should be small for the type of images that I call here the good guys. So these should be examples of nice high-resolution images that you would like the regularizer to favor. And it should be large for the images that you would like the regularizer to attenuate, that I called here the bad guys. And depending on the inverse problem you're solving, these bad guys could come from different places. I think the kind of you know, what we did and what makes sense actually for most of the things that I can think of is to just use a baseline reconstruction. What we used here is filtered back projection to compute a couple of solutions that you want your regularization approach to improve upon. Okay, so noisy reconstruction, for instance. And that's what the Wasserstein distance, the one Wasserstein distance, nicely does for us, right? So if I feed the regularizer with samples from the noisy distribution, let's say, the regularizer should be large and maximizing, and if I feed it with samples of the distribution of, let's say, ground truth images of high resolution, nice reconstructions, the regularizer should be small. Yeah? And so this is how we train, how we learn, how we parameterize a learned regularizer, and then we parameterize this regularizer with a neural network. And depending on the parameterization, the particular architecture I use for the neural network, I get also different structural properties for this regularizer. Okay, does it make sense? So one of the things we tried, for instance, is to use so-called input convex neural networks, which give you a convex regularizer at the end, right? Or the one that was most successful is the weakly convex version, which is a combination, I should stop, which is a composition between a smooth neural network and an input convex neural network. Right, and that's the recipe, right? How you train it. Let me just make this a bit briefer. Okay, and so here just the last example where I'm showing you how this works. So this is now for computer tomography, and I show you different types of reconstructions. Filtered back projection, total variation. Filtered back projection is the baseline reconstruction, right, that I started with, the noisy reconstruction. Total variation regularization we talked a lot about before. And then I'll show you one example of our learned regularizer that we called adversarial regularizer, just because of the fact that we trained it in this adversarial fashion between the good and the bad guys. And then I compare it with a pure neural network-based inversion approach that is called learned primal dual. That is, I would say, the kind of gold standard for machine-learned inversion nowadays, but it doesn't come with theoretical guarantees. Okay, so it doesn't come with with guarantees. So what you see here is the ground truth on the left and the reconstructions on the right. This is with the back projection. Forget about the numbers, not so important. I think visually it's much clearer anyway. This is what you get with total variation regularization. This is what you get with the learned regularizer. Right, and if I switch between the two, I guess it's pretty clear that you can get much more detail. And you can get it also with the deep learning based reconstruction, but you don't get any, you don't know whether, well, I mean, to say it very plainly, you don't know whether what you're computing here has anything to do with the data that you've measured, basically. Okay, the nice thing is, if you do it like this, you can do some mathematics, you can get some interpretability about the regularizer that you have learned. For instance, here we can show that it decreases the Wasserstein. So if you take a gradient step in the negative direction of the regularizer, in the negative direction of the gradient of the regularizer, then you approach the distribution of the good guys of the images that you want to compute, which makes somehow sense. This is what you want to do. You can actually prove that an optimal regularizer exists, so that this problem is actually well posed, and that a solution to this problem is a projection onto the good guys, which is another interesting thing. And then let me skip that, and let me just say, okay, you can get well posted. You're in a variational context. This is now what I'm showing you now is not rocket science and based on what is already out there. This is based on the classical variation regularization literature, but you can actually get well postedness for these learned regularizers and even a convergent regularization notion, right? Which is what I've explained before. And if you put some structure into this neural network like convexity, you can also get convergent iterative schemes for the variation problem in the end that you're solving. There are several extensions, right? With some people I talked about equivariant neural networks. It's very natural for regularizers to be invariant with respect to rotations or translations of your image, right? They shouldn't change, the regularizer shouldn't change what it's doing just if you rotate the image, and you can build that into the neural networks. And so on and so forth. I'll finish with this last example, just highlighting the importance of actually doing, if you do something learned, that you still want to do something that is mathematically rigorous, and also highlighting what the challenges still are. So this is now an example that is called limited angle tomography. So limited angle tomography is an example where, before with the sparse angle tomography, I'm leaving out every other angle or something like this, right? Limited angle tomography really means you have a whole wedge of angles where you have not measured the object, okay? So this is a highly ill-posed inverse problem. And you can see that, if you do total variation regularization, you can see the region in which you haven't seen, where you haven't measured the image, okay, which is here. You can see this fading out in the reconstruction. And actually with the filtered back projection, you can see it even better, right? Now the last three examples here are learned reconstructions, okay, where this one is this gold standard learned Pramodul reconstruction, purely deep learning based reconstruction. And these two are coming from this idea of learning the regularizer, okay? Now the problem with the first one is exactly this problem of not having the mathematical guarantees, because, I mean, it looks great, right? On the first sight, it looks great. If you wouldn't know what the ground truth looks like, you would say, wow, this is great. This is a limited angle problem. I've never seen a reconstruction that looks that wonderful, right? But if you compare it with the ground truth, you immediately kind of see that it actually doesn't reconstruct what is actually in the image, right? So it's not consistent with the measurements. You don't get that. And that is exactly where the lack of mathematical guarantees hits you. What you see in the second picture is another problem that might appear. So we have guarantees, we have mathematical guarantees, well-posted guarantees for both of these. But what you can see here is that even with learning, you can also get the prior information wrong. If you just, if, for instance, like in this case, the regularizer doesn't train properly because it's a difficult problem, and the data set might not be the right one, and so on and so forth, right? So there are many now other things that can go wrong. So the bottom line is, this is very promising, I think. We can get really great, really step-changing results to how we've done things before. But we still need to find this kind of sweet spot where learning and mathematical modeling are coming together in a both rigorous but also explainable way. Because the main thing behind getting this not right is, and not knowing how to do it differently, right? Okay, here we got it right. We used another, the only difference between the two is that here we used another neural network architecture. Okay. But what is needed is to really understand what these different neural network architectures and the associated training process is doing and how we can influence prior information we're introducing through training in a systematic manner, right? So different challenges are popping up in this context. So I'll stop here. I hope I could give you some examples of what mathematical imaging is all about, where things are going now, where the challenges lie. And thank you very much for your attention.
We're a little bit over time. Maybe just time for one quick question.
Are your minimization problem both convex or non-convex?
In this last example, you mean in the learned example, you mean?
Because you got the real positives 0, right? If your problem is non-convex, you cannot guarantee the uniqueness.
No. So if you don't have convexity, you can't guarantee uniqueness. You can get still existence. You can get stability, even in a non-convex setting. And in the weakly convex setting, which is this composition between a possibly non-convex but smooth function and a convex function, you can still get a convergent regularization. And you can get, for the numerical scheme, you can get convergence to a stationary point, basically.
But your minimizer is not unique. So you can expect this like multiple, right?
So you could. So this is another good comment, right? So the moment you have a non-convex regularizer, this is another additional ambiguity which you introduce, right? Because you have various different, depending on what your starting point is, you can get different types of solutions. Yes. So this is another. But in our experience so far, non-convexity is really crucial to get anything better. Okay. So just sticking to a convex neural network parameterization didn't really cut it. So it's not expressive enough to stick to a convex setting. And I can show you, I don't want to do it, but some of the slides I've skipped actually explain that. I can show it to you later.
Yeah, so because I'm wondering, is there any difference between saddle point, ground state, the global minimizer and local minimizer, and any difference if the problem?
Yes. Yes. So okay, what you do is, so what we also did is we for the non-convex case, we computed several solutions and checked how qualitatively they don't look very different to each other. So yeah. But that's all empirical, right?
Okay.
What I'm telling you here.
Yeah.
Okay.
That's where the neural network hits you.
Okay. So for the interest of time, so let's stop here and thank you, Carola, for the next talk.